Before getting into the technical derivation of what Lagrange multipliers look like, let's get an idea of what we're doing here. So what we're trying to do is we're trying to extremize a function over a specific domain. So in this case, like in this example here, we're trying to extremize the function z, or f, equals x squared plus 2y squared. And we're trying to do it over the domain x squared plus y squared equals 1. So this paraboloid here is a graph of f, and then if we graph the constraint, we see this red circle in the xy plane. So when we're constraining the function f to that, we're only looking for the points of f which are the points on the graph of f which lie above this red circle here, right? And well, what points are those? Those are the ones that actually intersect this cylinder, right? Because when we plug in a point from the circle in the xy plane, the point on the graph is directly above it. So we can see it as the places where the cylinder intersects the paraboloid, right? So I'm going to lower the opacity of the paraboloid so we can see that a little bit better here. So really what we're doing, in effect, is we're looking for the points on this curve of intersection, where the extrema are the highest and lowest points. So you can see 2 up top here and 2 on bottom here, right? So there's 2 maxima, well, there's, as long as those 2 are the same height, there's 2 maxima, and as long as those 2 are the same height, there's 2 minima, right? But the extrema are among these 4 points. So we need to know how to find those. So let's go up here and look at a contour plot of f. Those are the ovals here, the ellipses. And then inside that contour plot, or into that contour plot, we're going to plot the constraint, x squared plus y squared equals 1. And actually, for the purposes of this Mathematica demonstration here, I'm actually going to use negative x squared minus y squared equals minus 1. It's literally the exact same constraint, but it'll help, it'll make the visuals a little bit nicer here. So how can we tell, where the maxima and minima are, or where the potential ones are? So the way to see it here is you might notice there's these sort of 4 special looking points up here, over here on the left, over here on the bottom, and over here on the right, where the circle is tangent to the level curves of f. So those are actually precisely where the maxima and minima have to happen. And it's for the following reason. So let's say one could happen here. Well, since this constraint crosses that level curve, that means there's some places over here where it's lower, or maybe higher, depending on what these ellipses, what these level curves are. But since here, you can see this level curve is for a half, this one's for 1, this one's for 1.5. It's increasing as we move out. So if this were an extrema, well, it couldn't be, right? Because down here it's smaller, and if we go higher up this curve, it's bigger. But if we go to a place where it's just tangent to a level curve, it never gets bigger. And if we look over here, it never gets smaller. It never touches a smaller level curve, or up here, a bigger level curve. So this is why we suspect that the places where these are tangent should be the places to look for extrema. So we can see that that's supported by, so these orange vectors are the gradient of the function we're trying to extremize there. And we can see that it's perpendicular to both. Of course, it's perpendicular to the level curves, but it's also perpendicular to the constraint. right? And likewise, if we interpret the constraint as a function, another level curve, we can see that the gradient of that is also perpendicular to, well, of course, the constraint, but this time to the level curves. So we can see here that the gradient of the function we're trying to extremize and the gradient of the constraint are parallel here. So in the next video, we'll make an actual rigorous formulation of this and show that, yes, this is what we should be looking for and why. Okay, hopefully that made sense, and see you in the next video.